Hi guys, in this short video we're going to be taking a look at reaction mechanisms, taking a look at what they are and how we can show whether or not they are valid. So mechanisms are kind of like this human construct of imposed order on a reaction. We can't really see what's at the transition state, so the activated complex. It's usually really horrible and high in potential energy, so really unstable. It's stuff that you're not used to looking at. So a lot of mechanisms, when they're proposed, they have to fit some experiments. So I'm going to show you what that is. So first, let's take a look at the construction of a mechanism itself. So you're always going to have an overall reaction. So in here, this is all of what this is. This is two iodides and some H2O2 plus H plus yields I2 and H2O. So this is a redox reaction. And we have just the generic rate law that's been derived from experiments. So we have rate equals K, concentration of I, and that's going to be the first, and then H2O2, which is to the first. So overall, this reaction is second order, 1 plus 1. So a couple notes. The rate law that's right here is always derived from experiment. So anytime you propose a mechanism, in general, they're going to give you a rate law that goes along with it. So that's kind of fixed. That goes along with experimentation. If something doesn't fit your experiment, what good is it? It's really not too helpful. Be careful because the order and the stoichiometric coefficients are not necessarily the same. They can be if it's a part of the slow step, which I'll talk about in a second. But for the overall reaction, they may or may not be the same, so you need to be careful on that. The rate law in general reflects all of the chemistry down to and including the slow step in a multi-step reaction. So you can derive a rate law from the slow step, and I'll talk about that too. So here we have the reaction that we were just looking at, the iodide, H2O2 and H+. And this is one proposed mechanism. Are there others out there? Yes, this is just one of them. Okay, so if you look, every time that a mechanism is proposed, they're going to give you some details about how fast it's occurring. So we've got slow right here. Step 1 is slow. Step 2 is fast. Step 3 is fast. The other thing you want to look at is whether or not each one of these reactions is an equilibrium. And it looks like both of these are product driven, so that's okay. When you're hiking, for example, if I was going to go hiking with the class, I would be the slow kid. So if we're all going to reach the summit together, that means you all have to wait for me. I know it's a bit of a bummer. So what that means in terms of reaction mechanisms too is that the rate is going to be determined by the slow step. So it's almost like you ignore the fast steps, at least for now, and you take a look only at the slow step because this one is going to determine your rate. So if we take a closer look at this. So here's our same mechanism. We can see that this step here, step 1, is bimolecular because it's got two things that need to collide together in the correct geometry and orientation. And it involves two species. The first is the iodide. The second is the H2O2. Now, way back a couple slides ago, we were talking about how the rate law was given. It's given right here. And so this is rate equals K, I minus to the first, and then H2O2 to the first. And what we can see from the slow step is that the slow step matches the rate law. So if you take a look only at the slow step, see how you've got the H2O2? It's just written in organic chemistry-ish. And then you've also got the I minus. These are both to the first order. And so because everything here is going to be proportional, this is kind of a legit mechanism. It's a mechanism that fits the rate law, which is a good thing. The other thing that you can see here is that you've got a few intermediates. And the way you can tell that these are intermediates is because see how the HOI species is produced? And then over here in another step, it doesn't matter where, it's consumed. That means it shouldn't end up in your overall reaction, and as you can see above, it doesn't. The other intermediate is the hydroxide ion. You've actually got two ions that are being produced here, and you've got the consumption of two in the third step of the mechanism. So that means they're not going to be, again, they're not going to be in your overall rate equation, And guess what? They're not. So see up here, they are not. All right, so this is looking pretty good. Let's take another example. Here's another example where there's two possible mechanisms for a reaction between nitrogen dioxide and carbon monoxide. And it's got two possible mechanisms. So the first is just a single step, as in like they react, and that's it. The second is the creation of this intermediate here, and then the consumption of it here, so the carbon monoxide, right? So what you've got here is you've got same thing, the slow rate determining step. And if you look again at the slow step, do you see that? Two NO2s. If, and as only if, you have an elementary equation, that means a single step in your rate law, and if it is your slow step, you can derive your rate law directly from it. So what that means is you can use the coefficients as your exponents, similar to your equilibrium expressions. So that's pretty helpful. I just wanted to show you that. All right. So this is a bit more complicated of a reaction. So now we have a reaction of ozone itself turning into oxygen. So we have two molecules of ozone. This is going to be a bimolecular reaction then, turning into 3 molecules of O2. So with that, we can have one of two proposed mechanisms. Number one, this just happens. One step, get it over with. This is another proposed mechanism, and this is one we're going to evaluate to see, is this mechanism valid or not? Okay? So the first thing we're going to take a look at is we're going to take a look at the speeds of the reaction. So we've got a fast, and it says this one is equilibrium. So I guess I actually edited that arrow. So that should have been a double-sided arrow. I don't know if I can fix that. Oh, wow, that was horrible. Hang on, time out. Slightly better. All right. So fast equilibrium for the first step. And then we have the slow reaction being the second step, which is down here. They also have a rate expression, and that is given by experimental data. So again, there's no changing this. All of this has to yield this rate law. So let's look at a couple things first. First thing we need to look at to decide whether or not this mechanism is valid is we need to see if the overall reaction comes from, the summed elementary steps. So what that means is we're going to go in and we are going to try to cancel out some things like intermediates, catalysts, all of that jazz. Anything that's the same from the left to the right-hand side to make sure what we end with when we sum the step 1 and step 2 needs to look exactly like this, exactly like our overall reaction. So this is what we're shooting for right here. So let's go in and say, all right, we've got ozone here, no ozone over here. That's not canceling out anytime soon. We do have an oxygen that's over here, and you can tell that it's being produced and it's being consumed, so that's an intermediate. And then the O2s are going to stay together, and that's going to make our 3 O2s. So what we can do is we can cancel out that guy, cancel out that guy, and then we're good. So check. All right? The overall reaction comes from the sum elementary steps. So that works really well. The other thing that we need to do is we need to make sure that the rate law, which is right here, rate law matches. And what I mean by that is when we take a look at our elementary steps, so we've got step 1 and we get step 2, we have to make sure that the overall rate law for this matches the one that we get from experiment. Because again, if it doesn't match our experiment, then it's not valid. If it doesn't match what we can see, hear, we can run in a spec, we can do whatever we need to do. If it doesn't match our lab data, it's no good. So what we have here is we have a rate law. Just take a look at it. Rate equals K, concentration of O3 squared, over concentration of O2. Now, what I told you earlier was that, here, I'm going to get rid of those crossouts. What I told you earlier was that we can, from the slow step, we should be able to write a rate law directly from that should match this one. So this is what it would look like. Rate equals K. And then if you look, we have concentration of O3. And we also have concentration of O. Now, here's the question. Does the rate law that I just wrote match the one that's given in the problem? Certainly not. But here's the problem. See that species right there, that oxygen? That was an intermediate. Intermediates are never found in the rate law. So we need to figure out a way to get rid of this O, because there's a chance that when we get rid of this O, it might sub in some other stuff to make this rate law equal to this one. So I'm going to show you how to do that. Okie dokie. I basically just went, let's go back. The answer is OMG, yes it does. So another check. So as far as the question, is this a valid mechanism? The answer is actually yes, even though on first inspection, if we just derive the rate law from the slow step, it contains an intermediate, number one, that's how we know that we need to change it. It had the O. But if we sub in for the fast equilibrium, and it's always going to be fast equilibrium, by the way, so you can do the K1, K negative 1. So we can sub in for the O there, get it here. Look at that. Okay, here is our mechanism. And this is how we are going to handle this. All right, so what I want to do first is I want to be able to figure out a way to plug in for that O, because the O is an intermediate. I need to figure out another term that I could plug in for that instead. So what I'm going to do is I'm going to derive a rate law from my step 1, because that has the intermediate in it, and maybe through a system of equations I can sub that in. It's also equilibrium, which is going to play a very big role. So that's important to keep in mind. So there are 2 rate laws that I can come up with this. I can have a rate of the forward reaction equal to concentration of O3. So that's the rate of the forward reaction. I can also have a rate of the reverse reaction equal to, oops, I forgot K. I'll call that one K1. I'll call this one K negative 1 of O2 and O. Now the important thing to remember here is that this is an equilibrium reaction. And the definition of an equilibrium reaction is that the rate of the forward reaction equals the rate of the reverse. So what I can do is I can set these 2 terms equal to each other. So I'll have K1 O3 equal to K negative 1, oops, negative 1, O2, and O. Now again, what I'm trying to do is I'm trying to get O by itself. Because if you remember, the rate law that we had, which was this, rate equals strictly from the slow step, O3, and then O. That's horrible. I need to get rid of that. So what I'm going to do is I'm going to rearrange this, this set of data that I have right here. I'm going to rearrange this and isolate it for just the O. Then I'm going to plug that back into here and see if it reduces down to the actual rate law. So next thing I'm going to do is I'm going to do some rearranging, right? I'm going to divide over K negative 1 and O2. So now I'll have this K1 O3 over K negative 1 O2 equals concentration of O. Now, it doesn't really matter what's going on right here. These are going to get really confusing. They just essentially make a new K. K1, whatever it is, over K to the negative 1 gives you a new K. So I can collapse those down into, let's call that one, it'll be K prime. So, and I'm just going to flip it just for the sake of math so that I have like an X equals, you know what I mean? So I'll have K prime, and then I'll have concentration of O3 over concentration of O2. So now I'm going to take this, let's see if I can highlight it somehow. This term I'm going to take, and I'm now going to plug in for here, and I'll show you what that makes. I'll use a different color. So now I have rate equals the concentration of O3. Oh, there's a K in there, my bad. I keep forgetting those. So K, concentration of O3. And then I'm also going to have another K prime, concentration of O3 over concentration of O2. It's all coming together now. Because again, I can collapse the K's. Rate equals K double prime. Now I have O3. I'll just do it all out for you so you can see the whole thing. O3 over O2, which equals K double prime O3 squared over concentration of O2. Now, if you look back, what you're going to see is, so this is our ending result. Everything is all simplified as much as I can get it. And now I just have to say, does that match the rate? Everything is simplified out. We actually do get the same rate law, which is fabulous. So those are mechanisms. Those are how to show whether a proposed mechanism is valid. I hope you find it useful, and I will see you in class.